All right, guys. So this is the review for the first quiz. Is everybody ready for the quiz on Wednesday? Woo! Yeah, that guy's ready. That guy, 2 hands, nice. So quiz review today, it's going to be about an hour and a half. We're going to go over all the major concepts you should know for the quiz. We're going to go over some coding by hand examples, which are on every quiz. And if you have questions, feel free to raise your hand and everything like that. Logistics about the quiz are online, so we're going to split people up into different rooms based on their names. So if you have any questions about where to go or about what material is like the official word on what's going to be on the quiz, check online, and that's all up to date. So if there are no questions to begin with, we're going to start. And here's Allison.
Okay. Thanks, Rob. Appreciate it. Davin should have flipped to this. This is the non-exhaustive list of topics. As always, as Davin just said, consult the documentation online about Quiz Zero. But this is pretty much, it's on the syllabus. This is everything we've gone over thus far. Everything here is fair game, as well as anything else that may have been mentioned in lecture. My section here is just a lot of review. There's a couple exercises that you guys might work on, but for the most part, we really want to get to Davin with those code by hand exercises, so I am going to fly through this. If you have any questions, stop me, raise your hand. I promise I'll probably see you. If not, just wave it around. I'm going to be talking fast. I hope everyone's okay with that. Okay, official word. Davin obviously forgot to flip through these slides. Your intro, man. So tips for Quiz Zero, practice coding on paper. You guys are going to get some practice with that now with Davin, so you won't be completely by yourself. I think we're actually going through these 2 functions, so you'll be well prepared there. Be familiar with your problem sets. There have been questions on previous quizzes that will ask you, for example, to code up something very similar to Mario. So being very familiar with your problem sets, as well as the questions we ask you in the beginning on the forms that you fill out, will serve you very well. Do a previous quiz under the time constraints. These quizzes are long. The time goes really fast, and often you don't realize how fast it goes until you actually put yourself under those constraints. So if you can just carve out, 75 minutes either tonight or tomorrow to take one of these quizzes under that, you will be in much better shape. And also creating your reference sheet. Remember, you get 1 page front and back as reference for your quiz on Wednesday. Creating that is a great way to study. Anything that you're having trouble with, you want to include on there. Any things that your TFs have been like, this is really important, you should know this, are maybe things you should have on there if you don't have them memorized. Even if you do know them really well, sometimes having it on there is just kind of comfort for you, which I know quizzes are stressful, so any comfort you get can help. All right, also get sleep and eat and like the normal things that we tell you for quizzes. So starting off easy, data types and sizes. As I said, this is just going to be me throwing a lot of stuff up here that you should know. So we have, our chars that are 1 bytes, ints that are 4 bytes, longs, which are 8 bytes. Basically, it's just if you want to hold larger integers. Floats, which are 4, doubles, which are 8. Again, just gives you more space for your floats. And then type star, so any pointer on a 32-bit machine, which is all you guys need to know, is 4 bytes. So all things you should know, maybe things you want to have on your reference sheet. Okay, binary, conversion to hexadecimal, back and forth, all things you should know. So from binary to decimal, do you guys want to take a quick minute and try and figure out each of these and then tell me what they are? I also have candy in my bag, so anyone who answers gets candy, by the way. And I have lots of it. Let me grab this. I'm gonna give this to Gabe so you can hand out candy to whoever's nice and cooperative. Okay, I saw a hand there in the back.
Yeah, the first one is 42.
Yes, first one is 42, correct.
Who is it?
Second one, they're back in the yellow.
110010.
Correct. And this last one, down here on bottom. Yeah, also, you know what, just toss out candy. How about candy for everyone? And then the last one. Who wants to answer? Right there. 11100. 11100. Look at that. Congratulations. Great job, everyone. Okay. Everyone kind of understand the process for doing this. You have going from binary to decimal. The way I tend to do it is writing out the powers of 2. So I say, okay, 0 times 2 to the 0, so that's 0. 1 times 2 to the first is 2, going onwards that way. Does anyone want me to explicitly go through an example of binary? Okay, cool. Decimal to binary is very similar. I tend to write out the powers of 2, start with the one that is greatest, but doesn't go past the decimal that you're looking for, and then kind of work your way backwards, adding up things as necessary. And then with addition, it's just like normal addition. If you ever have the case where you're adding 2 ones, it obviously becomes 2. 2 in binary is now 1 0, so you need to carry your 1 into the next column. Cool. Hexadecimal, this might be something that is slightly less familiar. So as Rob was just telling me beforehand, his trick for this is to just split it up into 4 byte chunks. Okay? Sorry. See? Thanks, Rob. This is why you're here. Okay, so we just break it up into 4-bit chunks. So with binary to hexadecimal, we look at the first 4, which is, if we have 4 ones in a row, what number does that symbolize? F. So in this case, what is 11111111? Or what? Yes?
FF.
Perfect, FF. So great, candy for you. Now for hexadecimal to binary, we just think about it kind of in reverse. For each number or letter that we have in our hexadecimal, just convert it to its 4-bit conversion. So 5 in this case, what is 5 if we're representing it with 4 bits? And then A, which is actually 10, would be 1010. So we have that here. So converting between hexadecimal and binary actually isn't that bad. If you look at it in 4-bit chunks, it's going to be golden. Everyone, yes?
This is silly.
Uh-huh.
But, I always remember A, since A is supposed to be 10. In binary, it's just 10, 10. So.
Ah, there we go.
Hey.
Hey, candy for Rob. There is non-chocolate stuff in there, so you can have some. So ASCII math. Behave. So ASCII math. As you guys are probably well remember PSET 2 with Visionary and Caesar. You did a lot of this. Remember that characters are fundamentally just numbers, so we can do math with them just like we do math with ints. So we have just a little simple thing here. We have some int A that's initialized to 65, int B equal to the ASCII value of A plus 1, char C equal to D minus 1, and char D equal to 68. So then we are going to print all of them as we see here. And can anyone tell me what this will print out? Exactly. So one thing to notice is that we are printing out characters each time here. We are designating, even though A and B are ints when we declared them above, we are printing them as characters by the %C in our printf statement. So they will all print as characters. And of course, the ASCII value 65 will print in A. The ASCII value of A plus 1 would be 66, which would print to B. So in fact, we get A, B, C, D. Everyone good there? Any questions? Awesome. OK, scope. So scope is obviously a very important thing to understand here. A lot of you, if you have compiling errors and it says like you don't have access to some variable, it's probably because you defined it within a loop and then tried to access it out of it, or vice versa. So scope at its core is it just determines where we say a variable exists, where we can change it, where we can access it. It's just kind of saying these are the only places where you have access to this variable. So the 2 scopes that we talk about during class are global and local. So global variables we talk about when you are defining them above main. It means that your entire program has access to it, and it exists for as long as the program runs. Okay? Local means that it's more confined to a region. So whenever you have specific functions like swap, we always talk about swap with A and B. A and B exist within that function. They don't exist anywhere else. As well, when you have if statements or for loops, whenever we have, for example, in a for loop, we have int I equals 0, we have some condition and we update it. I only exists within the braces of that for loop. If you tried to access it elsewhere, your compiler would yell at you and be like, what are you trying to do? This doesn't exist. So that's the two different types of scope. Does that make sense to everyone? So for an example here, this is just some, simple program. What do you guys think is going to happen at each point that we try to print? So this one here, what's going to happen?
It will print 3.
Right, it'll print 3. What about here? It won't work. You're out of scope, right? Local variable doesn't exist outside of these braces. All right? And then what about here? Sorry, what? Rob, go.
I just said, global variable should be global underscore variable.
Ah, yes, sorry. Thanks, Rob. Rob's like our resident compiler. He'll just yell at us when we need it. Yes, that should be global underscore variable. So, assuming that that was global underscore variable, what's going to happen here? It'll work, so it'll print. So just very simple example. Okay, prototypes. So obviously we really emphasize for you guys to make functions if it makes sense in your programs. But of course, when you make your own functions, typically you'll define them after main and you'll try to call them in main. And if you don't use a prototype, your compiler will yell at you. Prototype is basically just telling your compiler that I have this function below main. I'm going to call it before I define it. Just hold on. I promise that it's defined, and you will have everything that you need. So the way we do it is just your return type, your function name, and your input list. It's basically the first line of your function declaration. It's really all it is. But this is just a general kind of format. So in our example here, which you guys should have seen in section at some point, we have some int cube that takes some int of input. And we have our main function, which calls cube. And cube is defined after the fact. So if we didn't have int cube in input at the top, when we called cube within main, our compiler would get mad at us. It'd be like, what are you talking about? Cube does not exist. I don't know what you're asking for, and I'm just going to stop. But because we did our prototype at the top, we've said, when you see cube, don't worry about it. I promise it's defined later, and it'll let you do what you want. So if you ever have a function that is declared after you call it for the first time, you need to have it prototyped at the top. Yes?
It's square, not cubic.
Oh my God! I did not. Gabe, I thought you were our proofreader. Okay, guys, bear with me here. I hope everyone's getting the idea. Okay. So this should have been square, not cube, but the idea remains the same. Any function that we're calling after the fact should have a prototype. Everyone good with that? Any other typos? Okay. Any typos here before we start, Rob? Okay, so structs. Basically, structs allow you to create your own data type. So much like an int or a char or a float, it's just another type. I like to think of it as like create your own data type. So it allows you to do that, and it holds different types of data. So if you remember, in an array, we can only hold things of similar type. Structs allow us to hold multiple things of different types. So in this case here, we have a struct called student, named here at the bottom, and we have some int ID and some string name. So this is just another data type. We now have a data type called student. So because we can think of it as just another data type, we can declare variables as we would any other. So instead of just having like an int student, we just have a student, student1. Oh, look, it's Rob. So here we're declaring a struct or a variable called student1 of type student. So it's going to have ID and name associated with it. And the way we access these elements within our struct is with the dot operator here. So in this case, we declared some student1, we assigned the ID to be 1, and we assigned the name to be Rob. Okay, everyone good with that? Use it just like, yes? So typedef just says that it's, Rob, you can correct me on this if I'm wrong, but typedef is just actually declaring it as a type that you can use, right?
Yeah, it's basically, so it's just creating an alias for it, a nickname for a type. So like you can typedef UNAT as byte. So UNAT already exists, and now we just have byte means exactly the same thing. And so here, we're typedefing some struct type to a name. So it's just a nickname for a given type.
String in the CS50 library was typedef like char star becomes string.
If you're, for our purposes here, like if you're declaring a struct, just do like typedef struct. Okay, so if we have so beforehand, this is just, a normal variable here. We access it with a dot. If we have a pointer to a struct, we can actually use an arrow, which is pretty cool. So in this case, we have a pointer to a student1 that is of type student. Remember, with your pointer construction, you want whatever type your pointer is pointing to be at the beginning. So we have some student1 here. And since this student1 is now a pointer, we can actually go student1 arrow name instead of dot because it's a pointer, and assign Rob. And now if we want to change Rob to Davin, this is just showing you a different way to do it. So instead of using the arrow, you can also, I will finish this and then take that question. You can also dereference student1. That's saying like go to whatever's at student1, which would be our student struct, access it with a dot and the element that you want, and then reassign it. There was a question.
Yes. So how come you have to use malloc when you're doing student star, but not when you're doing student?
Because this is creating a pointer. We're going to talk about that later in the review, so just hold on to that thought. If it still bothers you at the end, come talk to one of us. So these do exactly the same thing. We're just showing you two different ways to do it. Student1 is now a pointer, so you can access the name element within the struct with an arrow, or you can dereference your pointer and then access it as you normally would. Does that make sense to everyone? If like the whole pointer things are a little confusing, Gabe will talk about that, and then maybe this will make more sense. Yes?
Yeah, so how is this different from
The previous one? So the student1 in this case is not a pointer. It's just your actual like struct. Whereas this one is a pointer to a struct.
Okay, but does it kind of end up working the same as your out?
It effectively works the same. Your syntax is just different. Yeah. They are effectively the same. It's just depending on context, you may want one over the other. Yes?
When you're dereferencing student1, why do you have the parentheses?
Because student1 is the pointer, so you need to make sure you're just dereferencing the pointer. So in this case here, the parentheses around it means you're dereferencing student1, so you're going to where student1 points, which is like your struct. So now you can think of it as that struct, so we can use our normal dot operation. Any other questions? Cool. Awesome. So last thing, I think this is my last slide. Woo. Okay, so floating point imprecision. We talked briefly about this during lecture. Basically, we have infinitely many real numbers, and if any of you guys love math, there's all sorts of cool stuff with this. But there are infinitely many real numbers, but there are only finite many bits that we have, so you're always going to have imprecision, is all. And that's just kind of like something you should know, that like we may ask you, why does floating point imprecision exist? So just something you should know. And with that, I'm turning it over to pointers.
Hello guys, my name's Binky. I'm going to talk about pointers. Yeah, so pointer is actually my favorite part in this course. So just to make clear what Allison was talking about here, so the reason why the only difference here, the big difference was the way we declare things, right? So student star means this is a pointer to a student, whereas the slide before student is an actual struct, like an actual student containing those things. And the reason why we want to, yes, Davin?
What does the arrow mean?
The arrow means exactly the same as this. So you don't really need the arrow. Like if you're only programming in C, you can just use this. Sorry, I don't know what that is. You can just use this syntax. But some people, when they were designing C, they figured that people use that syntax so much that they will like just come up with a syntax trigger for it. And this took place in form of this arrow. And it's really nice because it symbolizes something like we're actually following this arrow, this pointer, towards some space in memory. And when we get there, we want to look to the name of that student, if that makes sense. Okay? So this is exactly the same. This is exactly the same thing as this. They get compiled exactly the same. Okay? And the reason here why we malloc something is because in this case, our variable is actually just a pointer variable. So we only have some space in memory that's holding a pointer. We don't really have any space that holds the actual struct. So this has to be done in 2 steps. We have to create the memory to put the struct in, and we have to create the memory to put the pointer in. So there are basically 2 different variables here. One of them is of type student, except it doesn't really have a name. And the other one is of type student star. And then student 1 points there, if that makes sense. Okay? So the reason why we use pointers is because everything in a computer, every variable in a computer has 2 things, right? It has its value and it has its address. And a good way to conceptualize this is there's many problems when you try to use functions, and we're going to try to look into one of those. Namely, it's good to think of memory as boxes, right? You always thought of variables. When you say int a equals 5, you think of putting 5 into a box, right? So what if you want to pass that int into a function? You just pass, I don't know, x into a function. But what happens is, normally as humans, you would think something like, I'm passing the box to a person. And that doesn't really happen in computers. What happens is you copy the value of the box to the person's box. So what I'm trying to say is if you have a function, here. If you have a function like 2.5 up there, if you try to pass a variable, it's just going to copy, if I initialize like int x equals 3, it's going to copy this value up to the variable a up there. Okay, and this is kind of the reason why we want to use pointers, because instead of giving just the value, instead of just passing just a value to a function, we want to pass by reference. What we call pass by reference is kind of giving the box to the function so that function can also change the values within that box. Okay, so just some basic pointer stuff is to create pointers, you just declare the type and you put a star right after it. And the type is just what you're pointing at. So if it's an int star, you're pointing at an int. If it's a char star, you're pointing at a char. If it's a student star, you're pointing at a student. Okay? And they're all 4 bytes long because this variable it doesn't actually need to hold a char, an int, or a student. It only needs to hold an address. That's why they're all 4 bytes long in a normal 32-bit machine. Okay? So here, x is a variable that points to an int, y points to a char, z points to a float. Any questions here? Cool. And there are 2 different symbols that I have to keep in mind when coming to pointers. So referencing and dereferencing are the big ones. So the ampersand, of the variable name gives you the address. So if you declare int a equals 5, then ampersand of a is going to give you the address. And you can actually try to print that and see what address in memory your variable has. And then dereferencing, so that was referencing, getting the address. Dereferencing is the exact opposite. Okay, just like times is the opposite of division, star is the opposite of ampersand. So dereferencing means go there. So if you give star of, I don't know, 50, that's going to try to go to the address of number 50 inside of your computer. Okay, and why do I say that they're opposites? Because what happens if you do something like star ampersand a? Well, ampersand a gives you the address of a variable, the address of a. But star means go there. So what happens if you go to the address of a? You just get to a, right? So going to the address of a is the same thing as a. That's why they're usually referred to as the same. This and this are referred to as like opposite operators. Okay? So cool. Under the hood, for example, if we declare int x equals 5, we have a variable. And remember that I said that every variable, and this is a good thing to keep in mind, it has 2 different things associated with it. It has an address and a value. Okay? So the value in this case is 5, and the address is, let's say, I'm making something up, it's 0x04. And the only reason why we usually represent addresses in hexadecimal is, one, because it's like good, it goes well with binary. It's easy to convert to and from binary, and it doesn't get too big if you have a very big number. So we like to use hexadecimal when printing addresses. But I could represent this as an integer, it's fine. And so it has an address 4 and a value 5. And then I said, int star pointer, so this is a different type, notice, int star pointer equals the address of x. So what is going to be the value of PTR? It's going to be the address of x down here. Okay? So the value is going to be the same as the address. That's the assignment operator doing. And then PTR is going to have its own address, which turns out in this case to be 8. Okay? And then I create a new integer copy, and I say int copy equals go there. So go to what PTR is pointing to. Well, what does PTR have? PTR has 0x04. What happens if I try to go there? I will find the guy who has address x and who has address 4, and who has address 4 is x. Does that make sense? Yes?
In this case, is the pointer in the stack?
In this case, it's good question. I didn't really think about this when making up these addresses, but if this is like all of these are local variables, then x is going to live in, everything is going to live in the stack. So everything is going to be pointing to stack. You only get to the heap when you start to use malloc, right? So if you recall, stack is every time you call a function in your program, like main, for example, or any other function, or printf, like printf, all of the local variables are going to get put in a stack frame, and they're going to get like piled up in the stack. That's why it's called a stack. And all of those local variables are going to be there. And the heap, and we're going to talk more about this later, the heap is where all of your allocator, your dynamically allocated memory lives. Cool? We good with this slide? Yes?
Why isn't int copy returning OX04?
Why isn't int copy returning OX04?
Why isn't that its value?
Because what is the value of PTR?
OX04.
OX04. What happens if you go to OX04? What do you get?
Oh, okay.
You see?
Yeah.
So you get 5. So copy is going to have 5, if that makes sense. Yes?
Could we have gotten 5 in the value box and copy if we put int copy equal to x?
And we would, yeah, that would have done pretty much the same thing. But this way we can pass address to functions, and that's the cool thing we're going to do right now. So this kind of exercise always comes up on, very, very usually comes up on quizzes, so it's really good to try to do that kind of thing yourself. So like try to keep track of what the address is and what the values of the variables are at each point, right? So this is exactly what we're going to do. Here we have steps 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we're going to keep track of the values of x and a. Okay? So what this is doing, this is a Buggy code. We're trying to do 2 5. So we're trying to get in a variable and change its value to 5, right? And remember my analogy of having a box and handing the box to someone. So main has this box called x, and it contains the value 3. And I'm trying to hand this box to 2 5, and I want 2 5 to change the values of this box to 5. Okay? And then I just print the value of x. Okay? This is what my function, this is what I'm trying to do. I'm just trying to update the value of of x to 5. Okay? Is it clear what the function does? Okay. So what are going to be the values of x and a right here, the first line? Right before the first line, I would say, of the program. Just garbage stuff, so I just put NA. So we don't really know, like a doesn't even exist yet, right? Because we haven't called 2 5. So int a is not declared. And x is going to exist here, but we haven't really assigned any value to it. So, okay. And then what's going to be the value? What are going to be the values of x and a in number 2? So x is going to be 3. That's easy, right? Because we're assigning 3 to it. And a still doesn't exist because a just lives in 2 5. So I'm going to have 3 and nothing. like garbage, whatever, okay? Not really defined, okay? And now this is the important line. Like here we're going to actually call to 5, okay? And remember what I said, we never pass in the box. We just copy the value of the box to another box. That's all computers do, copy things from one place to another. So to 5, what it actually does is it copies the value of x to a. So what is going to be here, the values of x and a? 3 and 3. We'll just copy it over, okay, from x to a. Cool. Now we're here. And now we're going to update a equals 5. What's going to happen in line 4? A gets updated, but x didn't get updated, okay? Because x still lives in main. It's a completely different block of memory. It's a different variable, okay? A is another variable. They happen to have the same value because I copied over the value of x to a. But now when I do a equals 5, it doesn't really affect x in any way. Okay, this is the trickier part. Does it make sense to everybody? Yes.
Question at 3, why is a already? Oh no, a is 3. Sorry, never mind. I read 5.
Yeah, 3, 3.
Never mind, yeah.
And then we assign 5 to a, but doesn't really change x. Good? Yes.
Can you explain again how a gets copied?
Okay, so when you call to 5 of x, so this line of code here, okay, to 5 of x, what is x? X is just 3 at this point, right? So you could just think of putting a 3 in here and forgetting about x. Just put a 3 here. Like, we're going to copy over the value of x to the int a that's up there, okay? So the value of x is 3. We're going to copy 3 over to a. And now this other block of memory, this other variable called a, will have 3 as well. Does that make sense? Yes?
If you gave Q5, like made its integer x instead of a, would that fix everything?
If it's an integer, no, that would not fix everything. So that's a very good question. It doesn't really matter what you call those variables. Again, it would be an issue of scope because they're not the same x. They're different. They're completely different spaces in memory, okay? So it doesn't really matter what you call them. That doesn't fix things, okay? More questions? Yes?
How does it pass back to number 5? Just print out.
Okay, we haven't done that yet. Let's go to number 5 then. What? We don't have a return out of main, but main returns 0 automatically if you don't return anything. Yes?
Could you make
We could have to5 return a, yes, but then we would have to assign x equals the return value of to5, which would be a slightly different problem. It would work. But what we want to do is what is called change something in place. So we want to actually change that box and not worry about having to return values or anything. Okay? This is just like the swap function David showed in lecture. Okay? Except I'm only dealing with one variable. And he used 2, so int a and b, and then temporary variable and whatnot. Okay? So what's the last line? After to5 returns, it's simply a is going to go away. We won't have a again. We won't have a anymore. And only x will still live on. And guess what? X didn't change its value after all, because we're only changing the value of a. That's why x was 3 throughout. Okay? Good. So this program does not achieve what we wanted. Now let's fix it. And the fix program is using pointers. What we do is we have 3 lines that are different. The first one is we're not passing x, we're passing the address of x. Okay? So instead of copying over the value of the box, I'm still going to copy over something, but I'm copying over the address of the box. So if I pass the address of the box to to5, then to5 will be able to find that in memory and change its value. Okay? So, and then up there, I have that a is not an int anymore. A is an int star. It's a pointer to an integer. And then, because I'm passing the address here, And then what I do is not a equals 5, because a is holding an address. So what I want to do is go there and update the contents of this address with 5. Okay, so let's go through all of the lines one by one. So when I start here, I still have NA, NA, NA for everything in the first line, because I haven't really declared stuff yet. Okay, and then line 2, I have x equals 3. A and star A still don't exist. Same thing as before. Okay, now it gets interesting. So I'm going to pass, and let's assume that the address of x is 12 in hexadecimal. Okay, let's just assume this. Okay, I made it up. And so what am I passing here to 5? I'm passing 12. Okay, so what value does A have? Sorry? Yeah, like let's assume that we are here now. I'm asking. It has been initiated because we passed something to the function. Yes? It's going to have the address of x, and the address of x is 12. Good? So x is going to be 3 because we haven't really changed x yet. And then A is going to be 0x12, so the address of x, because that's what we passed to 2.5. And then what happens if we try to go there? What are we going to find? So if we try to print star A, we're going to follow this address and get the value inside. And the value is just the same value that x has, because that's the address of x, which will be 3. Are we good? OK. And then now we actually go there and we update 5. We update whatever is in this address 12, we make it 5. So now both x and star A are 5. Okay? Why is that? Because the address of x is 12, and A has also 12 as its value. So if we follow 12, we're just going to find x. So whatever we do with address of A, with star A, is going to happen to x, because A contains the address of x. Okay? And this is like the crux of the fix. So now we're able from 2.5 actually access memory that lived in main. So this memory doesn't live in 2.5 like before, this address 12. And we were able to go there and change its value to 5. And then when we return, we forget about A, we forget about star A, and x is still 5. Okay? So if you want to implement a swap function, you would just do the exact same thing, except you need like 2 int stars here and so on and so forth. Okay? Are we good? Cool. So pointer arithmetic. This is a slightly tricky topic. So it turns out that pointers are just integers. You can think of them as integers because in memory you have like memory address 0, 1, 2, 3, 4, 5. So you can sum memory addresses. And that's usually what you do when you're in an array, for example. An array is just like a contiguous block of memory of lots of chars, for example, lots of ints. So if you want to go to the second int or to the third int, you can just sum something to the first address, and you're going to get there. So this is really useful for that. And the thing to keep in mind, though, is that it's not just like normal arithmetic, in the sense that if you're dealing with, say, an int star, and you add 1 to it, then you're not going to add 1 to the address, you're going to add 4 to the address. Because an int is 4 bytes. So this is just like walking on an array. If we have an array of lots of ints, and then we try to go to the second one, it's basically just summing the address of the first one plus 1. But that won't be just, let's say that the address of the first one is 4, here, in this case. And if we sum, so this is what's happening. We have an int x equals 5. X has its value 5. And we initialize this pointer, int star y equals the address of x. Let's assume the address of x is 4. What's going to happen now if I add 1 to y? It's going to actually sum 4 instead of just 1. So I added 1, but it actually added 4 because the computer is smart. So it's going to actually add by I times the size of the type of the pointer. Okay? So if it were a char, for example, if this were a char star, y, and if we added 1 to it, then this would be 5, because char is 1 byte long. Good? And finally, we got to pointers and arrays. It turns out that every time you're dealing with an array, you're actually dealing with a pointer. The very nice conceptual reason for this is that arrays are very big. So remember that I said that every time you pass stuff around, you copy everything. So if you have an array that's really, really big, you don't really want to copy everything every time you pass it around to another function, because that's like just massive amounts of work. So what you do is just pass the address of the first byte. And then the function will have access to all of the elements in that array. So you pass the array by its address, so the address of the first byte. So if we declare int array3 here, we know how to access the first element using the bracket notation. If you remember the bracket notation, array bracket 0 equals 1. Well, this would be exactly the same as just go there and put 1. Okay, it's exactly the same thing. So the bracket notation here will be the same as this line. And guess what the bracket notation for array bracket 1 will be? It will just be the same thing as this. So add 1 to array, move 1 along in memory, go there, and put a 2. Okay? And this line is the same thing. We want to go to the third box, so array plus 2, go there, and put a 3. So in memory, what's going to happen is we're going to have 1, 2, and 3 as the 3 elements of this array. We could have done this using our familiar bracket notation. I just want you guys to know that they're the same thing. Okay? Questions about this? Nice. Now we're going to hand it over to Hannah, talking about memory and other cool stuff.
So we're going to talk a little bit more about memory, which we just addressed using pointers. So there are two main parts of memory that we're concerned with. We have the stack, which grows up from the bottom, and the heap, which goes down from the top. And the stack is going to hold all of our instance variables. So each call to a function gets its own little frame on the stack. So as Gabe mentioned earlier, if we call the function again and again, we're going to stack things up on the stack. And similarly, the heap, which starts at the top, is going to hold all of the memory that we dynamically allocate. And so as we dynamically allocate memory, this will come down towards the bottom. A couple things to be aware of when we're using the stack and the heap. With the stack, if we have too many, let's say, recursive calls, and we're calling a function again and again and again and again, and it's stacking up, stacking up, stacking up, and it's going to crash into the heap, we're going to run out of memory, that's going to cause a problem for the computer, and that's called the stack overflow. So that's definitely something you should be aware of and try to avoid. And with the heap, you have to remember not to accidentally leak memory. Anytime you use malloc, don't forget to free that memory. Otherwise, it'll just be on the heap, wasted, and the computer won't know that it is free to use that memory. So those are a couple things to be very careful with when you're dealing with the stack and the heap. Any questions with this? Awesome. OK, cool. So this kind of has the same idea as stack overflow, where we're going beyond the bounds of what memory we're supposed to be able to use. So take, for example, a buffer, or you could just think of it as an array. And we said, OK, we're going to create this nice little array. It's going to be a string, or it's going to store characters. And it's just going to say hello, and it's going to terminate. That's it. But if I were someone evil and wanted to do something bad with this array, what I could do is try to write past the end of the string. And as you'll see, if I write far enough, I can actually affect the return address. And if I start to affect the return address, I affect how the program actually runs. And instead of returning, a happy string like hello, I could do something bad, like go to somewhere else in your computer, steal memory, change it, whatever I want to do. So that's what this would look like, is if I just kind of filled it up with random garbage values, in this case just A, and then when I actually got to the memory address, I started filling it with something that did what I wanted it to do. Any questions with buffer overflow? Awesome, flying right through this stuff. OK, so we talked a lot about pointers with Gabe. How do we actually get a pointer? How do we get an address in memory? Well, we can use this nice function called malloc, which is going to get a little piece in memory, specifically in the heap as we discussed, and it's going to give you back a pointer to that address in memory. And the argument that we have to give to malloc is how much space in memory we want. So you can see the size in bytes. Let's say, for example, or actually in this example, we allocate enough space for 10 integers. So probably what we're going to want to put here is an array of 10 integers. So we give it size of int, which we learned was how many bytes? 4, beautiful. And we want 10 of those in a row so that we have enough space to store all 10 integers in this case. Something super important, anytime you call malloc, you have to check for null. If you don't check for null, well, malloc, if it runs out of space and can no longer give you any more memory, it will return null. Okay? So if you don't check, malloc may have returned null, and then if we try to use memory that is null, or sorry, if we try to dereference a null pointer, we're going to get a segmentation fault, which we'll talk about right now. Awesome. Okay. Questions with malloc? Yes?
Does checking null give points / take out points if we don't do it on the quiz?
Sure. The question was, does it matter? On the quiz, will you get points off if you don't check for null? Yes, you will get points off if you don't check for null. Anytime you call malloc, both on the quiz and your p-sets and in real life, you have to check for null. Good question.
What if I don't free?
Gabe wants to know, what if we don't free? Then we will have a memory leak in our heap. Any other questions? Yes?
Can you go over buffer overflow real quick again?
Sure. The question was, can we go over buffer overflow really quick? Let's go back to the slides. So a buffer, you could just think of it as an array, right? You have some space in memory. And when we first create our array, we know arrays have fixed size, or our buffer has a fixed size. So let's say, in this case, we have just enough space to write the string hello. If we go past that bound, if we go past what our array we said it could hold, we could actually start writing into memory that the computer doesn't want us to write into. And specifically, if we hit something like the return address of the function, which, like any other piece of memory, is just somewhere in your computer, you can actually change that and start to do evil things. Answer your question? Awesome. Anything else? Yes?
So stack frames, you said grow from the bottom going up. Within a stack frame, does the memory grow from top down within each frame?
How do you defer to Rob on this one?
It will grow in the same direction as the stack grows.
Okay.
So I get confused because it's going the opposite direction.
Here.
This is correct. So if the stack is growing up, then generally, it doesn't have to be like this, but if you declare int x and then you declare int y, then int x will generally be lower on the stack than int y. But that's just a fact. That's not like an important C thing.
Yeah. So the question again was just, what happens, each frame builds up, so each function gets a little piece of the stack, and as you go up, within that little piece, within that frame, we'll say that variables within that frame also move up. Question?
Just to be on mic.
Oh, yeah.
Speaking to you.
Oh, yeah.
The exception is for arrays and structs, where arrays, a lower index in the array, and in structs, a higher field in the struct, are guaranteed to be at lower addresses than a later value in the array. So those are guaranteed, but any particular variables within, like int x and int y within a function, there's no necessary relationship between their addresses.
Another question over here?
Can buffer overflow only happen when you have like assigned an amount of an array that then is greater? Like, so if you're asking for something from the user, can they forcibly give you something back that's larger than whatever you've allocated for them?
Sure. So the question was basically, can the user give you more than you asked for? Well, you could prevent the user from doing that. You could specifically say, don't give me more than X number of bytes. I've only given you room for X number of bytes, X number of characters. So that's something you'd want to prevent. Yes?
What is the difference between stack overflow and buffer overflow?
Okay, so the stack overflow, what's the difference between stack overflow and buffer overflow? So we want to think of stack overflow happening when we're actually stacking up these function calls. Let's say you have a recursive function, because we know that every time you call a function, it gets its own frame on the stack. So we stack up too high, and then we start to overflow, and we use too much memory, and we don't have any more left. We get that error. Buffer overflow is within a program, we might not necessarily have run out of memory in the same way that we might if we're stacking up so many function calls, but we write past the memory that we know we can use, and that allows us to do evil things. Yeah.
Yes, you might want to just repeat this, but you can also think of a stack overflow as like a general or a specific type of buffer overflow. If you just think of your stack as a really big buffer, then when you overflow your stack, it's kind of like a buffer overflow, but stack overflow is just a specific term we use when the stack itself overflows.
Right. So to repeat for the video, you can think of stack overflow as a specific type of buffer overflow. Cool? Any more questions before we go on? Awesome. Okay, cool. So let's talk about some common error messages. This is something that has shown up on multiple quizzes, so something that's worth taking a second look at. I'm sure you've encountered at least some of these as you're doing your problem sets, so make sure you can talk about them on the quiz. So the first one is a segmentation fault, and that's any time we try to access memory that we're not allowed to access. So you might have seen this, for example, in Breakout. If detect collision return null, and then you tried to do something with that null value, the computer would give you a segmentation fault. So one important thing to do in order to try to avoid this is to always check for null. You might have also seen implicit declaration of function. So this is what happens when Allison showed you how we make a prototype, right? So let's say we have some function that we define, let's say cube, and that goes at the bottom of our function under main. If we forget to tell the computer about forget to tell the computer about cube, when main tries to call cube, the computer will be like, oh my gosh, I have no idea what that means. I don't know what to do here. So the prototype says, don't worry, I'm going to tell you, it'll come. Don't yell at me. Don't give me an implicit declaration of function. So if you get this error, one thing you're going to want to do is make sure you have your prototype. Okay? And last but not least, undeclared identifier is essentially when you try to use a variable that you haven't declared. So all of a sudden you start saying like n++, and the computer says, what's n? You never told me n was a thing. So one thing you have to make sure you did is tell the computer what n is. So for example, n might be an integer, and then you will avoid this error. Any questions on common errors? Yes?
For the implicit declaration of function, could it also be that you omitted one of the libraries you were supposed to include rather than the prototype?
Right, so that's it. So the question was, could you also get this error if you forgot to include a library? Absolutely, because in the same way that we want to put our prototypes before the main function, if we have a library, that's going to tell, those are going to essentially include the prototypes, include the definitions of the functions. Great question.
For segmentation fault, would that also happen if we tried to access a variable in a different curly brace than it was declared in?
Sure. So will we get a segmentation fault if we try to access a variable out of scope? Is that the question? Beautiful. So probably you're going to get an undeclared identifier error instead. So it's just going to say, I don't know what that is. Cool? Anything else? Yeah. Oh, OK. Beautiful. Alrighty. Recursion. So I mentioned a couple times that we might get a stack overflow because we're calling a recursive function so many times and we're getting all these stack frames, blah, blah, blah. What even is a recursive function? Well, a recursive function is any function that calls itself. Some things to be aware of when you are implementing a recursive function. Don't forget to include a base case. A base case is the point at which we end. So for example, if we're coding, say, Fibonacci recursively, we want to make sure that when we get to the 0th or the first Fibonacci number, those two numbers have base cases, because those aren't dependent on things that came before. Those have their own values. Okay? Some pros to recursion, which is a question we've seen on past quizzes. They can lead to more concise, elegant code, and a lot of different algorithms actually lend themselves to recursion. Their definition might be recursive in and of itself. So Fibonacci is one, factorial is one, merge sort is one, all things that you can look at. OK, any questions? Yes?
Is a corner case similar to a base case, or is that for some other kind of?
Sure. So a corner case is is corner case the same as base case? A corner case is anything that your code might behave a little differently. Base case is sort of related in that they're like particular cases that you want to look at. But the idea of a base case is that you want your recursive function to stop. At some point, it can't keep calling itself forever. It needs to stop at some point.
Yes, frequently your base cases might be examples of corner cases.
All right. Cool. Anything? Yes?
Can you explain bases a little bit more?
Okay.
I don't quite understand the idea of bases.
Base cases?
Base cases,
Oh yeah, sure. Let's see, do we have chalk over here? Yes, we do. Okay, so really quickly, I'll try to write big enough so you can see it on the screen. Let's talk about really quickly Fibonacci. So I'll give you the Fibonacci sequence. You can look up the definition. Essentially, each number in the sequence is the sum of the two previous numbers. Okay? So the way that I just described Fibonacci, you could hear the recursion, right? When I said each number is the sum of the two previous numbers, we could say, okay, well, the nth Fibonacci number, so let's say we have this function called fib of n is going to be equal to fib of n minus 1 plus, sorry, we'll go on to the next line over here, fib of n minus 2. Okay, so this works great if you're looking at, for example, the 0, 1, 2, 3, 4, 5th Fibonacci number, where you can say that 5 is equal to 2 plus 3. But what if you're at the beginning? What if you're just hitting these first two values? To get this 1, you can't say add the previous two, because that's 0 and I don't know. So at some point we need to stop. At some point we need to say that these two just have their own definitions. The 0th Fibonacci number is 0, and the first Fibonacci number is 1. So the way I might code this, I would say if n is less than 2, then just return n. And that would be my base case. That's how I know to stop with a recursive function. Is that clear? Awesome. Anything else in recursion? OK, beautiful. Let's quickly talk about search and sort runtimes. And then I will give Davin some time to talk about coding examples. So here are the main search and sorts that you should know about. Guarantee, or I can't guarantee because I haven't seen the quiz, but this comes up quiz after quiz after quiz. So definitely use this chart. Like, take this chart, put it onto your cheat sheet. You will be a happy person. This tells us the runtimes of each of these sort and search algorithms. So linear search, you can see runtime, and same with binary search. Go over what these algorithms do, the general idea, look at some pseudocode, if not code itself. You'll see that bubble sort has a upper bound in the worst case of n squared. So if our array was completely backwards before we wanted to sort it, we would say that that's going to take n squared steps. But in the best case, so the lower bound for the best case is going to be, if it's already perfectly sorted, then all we have to do is check that it's sorted. There's a question over here? When would you want to use selection sort? This one, the one that's n squared in both cases? So it's very different. If you have specific requirements for your program, like things like if we just said implement a search, or sorry, implement a sort, you'll probably want to go for one of the ones that has a best case of n, or a lower bound in the best case of n. But there might be certain things like, say, swaps are really expensive for some reason. Then you wouldn't want to do bubble sort because you have to do so many swaps, things like that. Any other? Yes?
Would it be enough to say that using that before
That's one thing that would tell you if you're looking at the implementation. The way I would actually think about why it's n squared is that we have to run through our array of length n, each time making at most n swaps. And we have to do this process n times. So when you have to make at most n swaps, and for n runs through the array, this is going to be n squared. But yes, this will be revealed through this double for loop as the question asked, or nested for loop, I should say. OK? And then merge sort, which is the fastest sort we know, or that we've covered in CS50, know that the main algorithm is this idea of breaking into sorted pieces and then merging together these sorted bits. And that'll get us n log n. Any questions on searches and sorts before I pass it on? Let's see. Oh, linked lists. Sorry, I have one more topic. OK, awesome. Linked lists. Problem with arrays. They have a fixed size. So if you don't know how big your input is going to be, you don't want to create an array. Because if we create an array that's too small, we might run into buffer overflow. So instead, we could do something with linked lists, which allows us to have a dynamically sized data structure that will allow us to store a more flexible amount of data. So within each node in our linked list, we have two pieces. We have the actual value that it stores. So that's just the thing you would see in the array, for example. And then we also keep track of a pointer to the next thing in memory. Unlike arrays, which we know are all going to be, array elements are all one after another in memory, linked lists could be anywhere in memory. They're arbitrary locations. So in order to actually go find them, we need to keep track of the next thing in our list. And then in order to know where that list as a whole is, all we have to keep track of is the very first element in our linked list. And that'll allow us to follow through. OK? So this is how you might define a node. This is a great opportunity to take advantage of structs, because you have this idea, well, for a given node, I have two pieces. I have the actual value itself, and then I have a pointer to the next element in the linked list. So you see we have an integer n, which is going to be the actual value, and then a pointer to a node called next. So that's going to be the next element in our linked list. Yes?
You have to specify that node star is like a struct.
Yes, so since this is almost like a kind of, it seems like a recursive definition in that we need to know what a node is inside defining a node. Since it doesn't actually know what a node is completely until we get to the end of this, and after this we can just call it a node, inside of this definition we need to call it a struct node. Great question. Anything else? Yes?
And why do we have to say node twice? Because when we were defining a student, we just had student semicolon at the very end. But now we have to type that struct node.
So I believe in the last example, we were just creating, anytime you wanted to use a student after that, you had to use struct node. I'm sorry, struct student. This allows us to, after the fact, just use node as a new type, essentially. Does that make sense? So we'd have to go back and look at the code before, but I would guess that we didn't use typedef, and we asked the question, why do we need to use typedef? Typedef allows us to avoid the word struct in the beginning. Yes?
What sort of questions would come up in terms of nodes and other linked lists?
So one thing is, we could say, how might you search through a linked list? OK, because it's a little more complicated than if we're searching through an array, we can just look at element 0, element 1, element 2, blah, blah, blah. If we wanted to search through a linked list, we'd actually have to follow this little maze of pointers. So let's actually go through this really quickly. What we could do in order to, let's say we wanted to just iterate through our entire linked list, we would start at the head. And then in order to move to the next element, instead of just incrementing by 1 like we might in going through an array, we're actually going to follow the next pointer. So we can find where in memory the next element is. So I know it's not enough to take all of this in right now, but you'll have these slides so you can go through this a little more slowly. But essentially what we want to do is follow these pointers through the entirety of the linked list. So this is a question you might be asked. Something to notice with insertion, let's say we wanted to put a new element at the front of our linked list. We have to be very careful about the order in which we reassigned the pointers. Because let's say I just said, OK, make head point to this new element. Just make it point to 1. Then we've essentially lost the rest of our list, because I don't remember where 2 lives. So we have to do it in a very specific order. First, we make the new element point to the head, and then we make the head point to the new element. So let's see what that looks like with arrows. Just like that. So you first have the new element point to the old head, and now we have the head point to the new first element. Any questions with this? OK, here's some code. Again, something to look at a little bit later. And now I will turn it over to Devin for GDB and a little bit of practice coding on paper. Beautiful.
And Rob.
Oh, Devin and Rob, I'm sorry.
Do you want to say the node thing real quick? Yeah. 1 second. OK, while Rob puts the microphone on, so what's GDB? Everyone should have seen GDB in class and also at office hours, and you should be using it. So what is GDB? Anybody? It's a debugger, and what does it allow you to do? Like, why do we like GDB? Right, so you can walk through it at like a human pace. And so what are some commands you can do? Well, break is probably your favorite command, because that lets you break the program and actually walk through it line by line. Run allows you to run it. Next, like stepping through. What's the difference between next and step? Wait, say that loud. That was correct. Yes, awesome. So like next and step, if you're like, let's say you have a function that you define, let's say sum, in your main function and you're just hitting next, 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 you're actually gonna execute that function, but you're gonna jump over it. If you hit step or S or whatever, you're gonna actually jump into that function, and then you can hit next to see the different calls inside that particular function. Yeah.
Is there a way to jump like back out?
Finish. Yeah, finish will jump you out. So it's going to finish that function, and then you're going to be back in main, for example. Print, we'll print it out one time. Something I always use is display. Display will print it out constantly throughout the entirety of your program. For example, if you're in a for loop and you want to see how something's changing, and you don't want to like constantly be doing like print, 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 display will display that variable continuously every time you hit next. And continue. So GDB, that's GDB. Yeah. Oh my, what is it? What's the local variables?
There's something that's like locals or something.
It might be something like that. Yeah.
Info locals?
That's it. That's the one. Yeah.
Yeah.
What does continue do?
So it's just going to continue your program. So if you break and hit continue, it's going to continue. It's going to just run that program until it hits that break again. So for example, if you broke in a function and you're going to do like for loop or something like that, and you hit continue, it's going to continue and go back to that break. Or if there's no break, it's just going to continue and finish the program.
So just like run stops at the very first breakpoint you hit.
Yeah.
If you then hit continue, it'll keep going till it's the next breakpoint, and then continue will go to the next breakpoint.
Any other questions on GDB? So I think in the past we've asked you what GDB is and give an example of some things you can do with GDB. So real simple, but yeah, there you go. And nodes?
Yeah. So which direction was it?
Wait.
This guy?
That one.
This guy. Oh, I didn't realize. So we weren't clear on what I don't know who it was, but the question, we don't know exactly what you were asking about it. So just to clarify something. So first, like I said before, typedef, you're always using just to create a nickname for a type. So right here, the nickname we're creating is for this type struct node. So first, ignoring this node in the typedef. So this struct node curly brace down to the next curly brace is the struct node type. And we need that node up there because we need to reference node in here. So with this sort of recursive struct, you need to give this struct a name or else you couldn't say struct node in here. Whereas before with student, when we were typedefing, we didn't have to say student up there because we didn't need to we didn't have to say struct student inside the struct itself. So it's the recursiveness that forces us to say node there. This node is just the name we're giving node for the typedef. So that node is not the same as that node, but this struct node is the same as that struct node.
So whenever you call like node in your main function, you're not going to have to say struct node. You can just say node because node is is basically you're saying, okay, instead of having to call struct node in my code, I just want to rename it as node to make it easier.
If you always use typedef, then this is the only place you're going to have to declare a variable with struct node. Star.
Yeah. Okay, so the last part, it's hard to teach because, what? Because it's coding on paper. So every year we have code on paper questions. So I think last year, 12 out of the 80 points were code on paper. The year before that, 10 out of 80. The year before that, 20 out of 100. So quite a few of these. So you're going to have to be able to code up these functions by hand. So I figured we might go through a couple of them and see how people do, kind of walk through them slowly with people. So generally, strlen and A2I have been very popular. Last year, I think we had get positive int and random int. But pow, so power, also a positive one. So let's just go through maybe one or two of these together. What do people want to see? A2I. OK. I'm going to do it on the board. Do you have a preference if I do it here or there? There, Gabe says there.
And just as general thoughts on these coding questions, try to write something. Don't leave it blank. If you can get the return type correct, or maybe we might give it to you, but if you like write the general function signature, if you can get the base cases correct or corner cases, or remembering to check for null, as long as you have some things, then maybe we can give you a couple points for the problem. Don't just leave it blank.
Yes, and if you are just completely stumped at how to actually turn it into code, if you write pseudocode, that's pretty good too. So if it's a 6-point question and you write the correct pseudocode, you'll get at least 2 points. So don't just leave them blank. Try to put something.
It needs to be the correct pseudocode,
yes.
though. So we generally are less lenient with bugs in pseudocode.
OK, so you guys wanted to see A2I. OK, so just really Okay, so what you want to do is you're going to be given some kind of number, but this number is not going to be an int, right? What's it going to be? It's going to be a string, right? So if you're given a string, let's say...
Should I pull up an editor? I could pull up.
Oh, you
Would you
want to
prefer the word?
What do you want to do? I mean, you want to do it by hand, or do you want to do it by computer?
Do it by hand. Do it by hand.
Okay, so it's going to be a to I. So what's it? I mean, we'll probably give this to you, but what's it going to return? It's going to return int, right? So I don't want to do it there. I'll do it here.
You can pull it down and then push it up when it.
Oh, yeah. Game change. Okay, so it's going to be int a to I, and what's it going to take? A char star, so just a string star s, like
Nice
that.
star.
Nice. This might not be done. Okay.
Yeah.
Okay, so the first thing you want to do, I don't know if anybody have looked at the practice solutions, but what you're going to want to do is you're going to want to have a loop, because you're going to want to actually step through this string. So helpful. So let's say we're going to have a for loop, and we're going to step through every element of the string. How long is that? How many times are we going to iterate in that for loop? Strlen, yeah. So let's say int length equals Strlen s. And just curious, why is it always kind of better to do this outside of loops? Like, why is it better to call this function outside of a loop? Just a quick sanity check. Yeah. Exactly. So yeah, exactly what she said. So we don't have to keep checking it. So for example, if I'm calling this function inside a loop, then I'm going to keep calling this function multiple times, and that's going to decrease the efficiency of your program. So it's always useful to declare it outside.
That said, on any of these problems, pretty much as long as you get a working solution, you get full credit. So don't worry if your design is absolutely horrendous. It might make us upset reading your code, but as long as it works, you'll get the points.
Yes. OK, so then I'm going to declare some variable. It's just going to call int sum. And I'm going to set this equal to 0, like that. And that's just going to be a placeholder. So that's going to be what I'm going to return. So I'm going to eventually return sum out of this program. So I have these two variables. I have length. I have sum. And now let's jump into our string. So let's have our for loop. So for int I equals 0, while I is less than length, I plus plus. And now, nice. OK, and now here comes the meat of our code. So you can actually do this basically in one line. So does anybody have an idea of what we're going to do next? OK, so it's OK. So we're going to say sum equals, let's get this over. Sum equals sum times 10 plus, we're going to take s I minus 1 quote 0 1 quote done, like that.
Very intuitive.
Crushed it. OK, so someone, OK, so this, I got it. OK, so this is clearly going up. What does this mean? So does anybody know what this means? Can everybody see this? No, nobody can see this. OK. OK, I'm going to
write the formula just right here.
OK, Rob's going to do it on the computer, which is fun.
Oh my god. Or I won't.
Stand by. Yeah, sure.
We may have some of that answers already, but why do we declare int length with Strlen s instead of just using Strlen s inside the for loop?
OK, so it actually, like, just in general, if you were to put, like, in this declaration, like, int I equals 0, comma, length equals Strlen, that's fine because that.
Why do we even need to use length? Why can't we just have used strlen s like the whole time?
You mean like right here?
Yeah.
Because every time this for loop runs, it's going to evaluate this condition. And if you have strlen there, then it's going to have to actually call that function every single time. So instead of just comparing it to an int, you're going to be calling a function and then comparing it to the return value. Yeah, so it's just, yeah. Nice. OK, so now that everybody can see it, what does, this is it. This is the jam right here. What does that mean? What am I doing? Yeah, an idea? Yeah.
So when you're iterating through, you're going to be going from left to right, so you're going to be going like in decimal from down the base 10.
Exactly.
So each one you have to multiply what you saw as the value of the int by 10 because you have to move that over once.
Perfect. Perfect. So for example, let's say I gave you, I'm going to write over here. No, I'm not. I'm going to write over here. Let's say I gave you 76, right? Let's say I gave you 76. That's a string to begin with, OK? So length is what? 2, right? Sum is 0. OK, then we jump into our for loop. OK, the first iteration of this, what's it going to be? It's going to be sum is 0, so sum times 10, 0. That's meaningless. Then what does this do? It's going to turn that character into an integer, right? It's kind of like with your problem set, this light. It's kind of like with problem set 2 Visionaire, you're dealing with ASCII values. So if I give you like a 7, but it's a character, and you want to know, OK, what digit is that? Yeah, you could, yeah. So what digit is that? You can subtract 0 from it, but you have to subtract 0, the character. And where some people get tripped up, they're like, OK, well, do I have to know the ASCII values for this quiz? No, you definitely don't need to know the ASCII values of like lowercase a, uppercase a, 0.
There is no reason to ever put this on a cheat sheet.
Definitely do not waste your space with this. You can literally just, instead of saying 48, like right up there, that is perfect. That is equivalent to saying 1 apostrophe like that. Exactly the same.
You can almost think of it as if, God, I need my, oops. You can almost think of it as if we have something like a hash define 0 as 48. That won't work, but think of it as single quote 0 single quote, and for all characters, think of it as a constant that represents that ASCII value.
Yes. OK, so the first time through, so with 76, so the first time through, this is just the character 7 minus the character 0, and those are 7 integers. Well, those are 7 spaces away from each other on the ASCII chart or whatever. So that's going to return an int of 7. So now sum equals 7. OK, well, let's jump into this for loop again. OK, now it's sum times 10. So you're effectively moving the 7 to the left. Does that make sense? You're effectively moving it to the left, and then you add, this is going to be 6 minus 0, that's 6. So it's going to be 70 plus 6, 76, that's your number. So regardless of what number I give you, it's literally just going to shift the larger values to the left, 1 factor of 10 each time in the for loop, and then add on as necessary. In the back.
We don't have to do any checking for this program?
So as far as checking goes for the program, we would tell you pretty much what you need to check. If we don't tell you anything, then generally assume you have to check most things. Like you might, just to be safe, you should probably check, hey, is S null? Then I have no idea what to return. But we would tell you this sort of thing. 0. I don't know.
And why would you want to check if S equals null? Because it's a char star. It's a pointer. So a perfectly acceptable declaration, I could say, OK, S equals null, because it could be a pointer to null. So whenever you have pointers and you're passing them in like this, you should probably check. Because if you don't check that, and then you then go into your for loop, and you're doing, scoot down.
Sorry.
And so like if it is null, and then you do this, what error are you going to get? You're going to segfault, right? Because you're trying to index into null. So you're going to try to index into memory that you don't own. So this, if this is null, and you do this, you'll segfault.
I also think on the exam in which we ask this question, we tell you that you can just assume it's a positive number, because A to I is also expected to handle negative numbers. So you would have to special case, hey, is the first character a dash? In which case, OK, now it's a negative integer. But we'll tell you these sorts of things. We'll tell you what you need to handle.
Yes. So I'm sure some people might have, if you started looking at old exams, you've seen Sterlen. That's a popular one. And I think in Sterlen, you had to do this check for null, the return 0 or something like that. Like you had to check for null, and if you didn't, that was a point off on the quiz. So anyway, does everybody feel okay with A to I? Does anybody want to go over parts again?
Oh yeah, I think we also tell you you can assume that everything is that they're actually entering a number, that you don't have to worry about like letters being in the string. So
yeah, yes.
Can you clarify one more time when you use double quotes and
Sure.
single quotes?
So double quotes, very simply, is double quotes are strings. So if you double quote anything, that's a string. So like if I had this 0 over here and I did this, that's a string. That's no longer a character. So I can't find this value on my ASCII chart because it's a string. Yeah. OK. Any other questions? Yes?
So I already answered this, but just like when we're actually writing this quiz, you want us to like put a slash with zeros to indicate
No. The question was, should you put a slash to the zeros to indicate if they're zeros? No, we'll figure it out. Yeah. Thanks. Good. Yeah. OK, anything else? Does anybody want to say? So I think we've run a little bit over time. Do you want to see another one or? Random ints. OK, exactly. So let's do random ints. I'll do it over here. So random int is actually much simpler. I think A to I is probably the hardest one that we've asked in the previous years. What?
I'm seeing if it's kind of viewable from over here.
Is it?
I don't think it's gonna. I think it's gonna run off to the right.
OK, so I'll do this one, and then you can just put it on the screen.
All right.
You want to be my scribe?
Yeah.
Nice. OK, can I erase this? It's so hard.
Yeah.
You do what you do, and do what you don't. All right. OK, if I remember correctly, on the quiz, the random int was like, OK, I'm going to give you two numbers, like an A and a B, and I want you to give me a random int between those numbers. So random int is going to take two numbers. So random int, and it's going to return an int. So what's the return value? I just told you. Int, right? Like this. And then it's going to take two ints. So it's going to take int A and int B, like that. So what random int is going to do is it's going to return some random value in between these two values. So it's going to be greater than A, less than B. So I think you can probably assume that A is the smaller of the two values. So if we're dealing with randomness, what function have we seen that gives us random things? drand, exactly. So you're going to probably want to use drand. So you can say int random, and we'll just say it equals 0 right now. Then we're going to say, OK, random equals drand 48. And what does this return? What does this function give you? Yeah, between 0 and 1. So it's going to be.
And this is, I think we would tell you this. Like you can use drand 48. You can verify this on the past exam. But we'd probably say you can use drand 48, which returns a float between 0 and 1.
Yes, yes. I'm pretty sure on the exam it says you probably want to use drand. Yeah. So it's going to return some value between 0 and 1. And then what are you going to want to do? Well, you want to multiply by. Wait, I think it's like this. Sorry. I'll just do this. I don't know. So b minus a. So why b minus a? So let's say drand gives you back up, and then okay. So I'll just do the rest. So plus a. So why is b minus a? So let's say that drand gives you back the maximum value it could possibly give you. What's that going to be? 1, right? So if this is 1 and you're multiplying it by b minus a, well, that's just the difference between b minus a. And if then you add that back onto a, that is what? It's basically b. Does that make sense? So if this is the maximum value it could possibly be, it's going to be 1. And then this is just the difference between the two, add on A. So this is going to return random. And in the corner case that drand gives you back 1, this is random will just be effectively be B. But that's the maximum it can be. So if it's going to be less than that, so let's say it's like 0.9. So then 0.9 times B minus A is going to be less than the difference between B minus A. And then if you add that onto A, then that value is going to be greater than A because you're adding something onto it, but it's going to be less than B. So you're going to get a random number because you're calling drand, and that random number is going to be somewhere in between A and B. Does that make sense?
Just to put it in concrete numbers, so let's say we want to pick a random number between 7 and 10. So B minus A is our range. So there's a range of 3 numbers we want to choose from. And then multiplying that between 0 and 1, if that gives us, let's say that gives us 1.5, then 1.5, we want to go from 7 to 10. So 1.5 plus 7 brings us back into our 7 to 10 range. And then we're storing it inside of an integer, so it's truncated down to 8. And then we just return that. So B minus A is our range. A shifts it up into the numbers that we want within that range. So between 7 and 10, and then we can return what we end up with.
Yeah. Nice. Thank you. Yeah, what's up?
Do we run into any kind of casting errors when if drand is returning a float?
So just like Rob said, because random is an int, so drand will be a float. So, and then it multiplies out. You might get some kind of float numbers, and then it's going to truncate.
Yeah. If the compiler were to warn you about like loss of precision, just throw an int in there, and then it's good.
Yes.
So I'm actually wondering, is random int supposed to be a number from A to less than B? Like if it's between 7 and 10, what are the possibilities? 7, 8, and 9, or 7, 8, 9, 10?
I forget. On the problem
I think
set,
it's 7, 8, 9.
It specifically says one's inclusive and one's exclusive. But
Yeah.
I don't.
So I think B is not included, in which case there's an equal probability of 7, 8, and 9. There's no probability of 10.
Yes.
I have a question. We want to define a function that returns not one value but an array. Then what would be the syntax after return?
OK, so then you would, after return, so you would just, so let's say you had declared an array somewhere up there, then you would just return the name of the array. Oh, wait, so sorry. The question was, how do you return an array?
Though it couldn't be an array declared on the stack or anything like that. It would have to be something mallocked, because malloc is how you get around the automatic memory allocation.
Yes.
How you get around local scope.
But you would just return its name.
I want basically kind of function that just returns not one value, for example, 2 numbers. So I want
You can't return multiple numbers. You can't like return a. So.
I thought about returning an array or something like that.
Yeah, so the question is, can I return multiple values? You can't return multiple values. You can't like return A, then return B or something like that, because after you return out of the function, and then the function is done, and like Rob said, it's on the stack, so all that memory just gets returned to the computer. Everything gets forgotten, basically. So if you want to return multiple values, you have to return an array, and the way you do that is mallocking, and then you would return X like that. Basically, you just return the name, and when you return something like this, you're not actually returning the values. So let's say you stored the values in an array. You're not actually returning those values. Like if I returned an int, I'm really returning copies of the values. But if I return something like this, I'm returning a reference to those values. So I'm returning basically a memory address to those values. Does that make sense? Nice. Yes? No. No, I don't think so.
Yeah, so do you have to say anything about srand? The default, if you never say srand at all, is to just do srand of null. So drand on its own will work, and it will just automatically seed with the current time, is what it uses.
Yes? Yes, you can.
So you could say like 4 times 2. The thing is, you cannot assume that an int is 4 bytes. The only...
I mean, for the quiz, you can.
No.
Yeah, no, yes, you can. If they ask you how big an int is, you can't be like 4 or 8.
Oh, so if the question is specifically like, if it is a coding problem, you should say size of int. If it is a table where it says how many bytes, you shouldn't fill in size of int.
Right, so why is size of int important here? So like if we're working on a 32-bit processor or something like that, then it's going to be 4 bytes, but on some of the newer stuff, it could be what? It could be 8, right? So this, if you just hard code 4, then on some machines it will work, some machines it won't work. But if on the quiz we're like, how big is an int? Put 4.
Yeah. Right.
Yeah.
So because we're declaring using malloc inside a function, should we put 3 inside that function, or can we use it outside?
You can use it outside that function. So he's asking for free.
Oh, yeah, the free does not happen. That's part of the magic of malloc, is that you're not restricted to local scope. You have full control over how long your variables live. So we declare, or we call malloc here. It might be a completely separate function. It might be 10 hours later that we finally call free.
So for example, like a couple weeks from now when you finally do your dictionary speller presets, you're going to have some function that creates tons of nodes. So you're mallocing tons of nodes in this function. And then later in a separate function, you're going to want to free all those nodes. So you can literally just pass to free a pointer, so a memory address, to what you mallocked, and that will be fine. You don't have to free like in the same function. Yes?
So a malloc variable is never local. Like you can always reach it outside. Is that what you're saying?
Wait, say it. Sorry.
If a malloc variable can be freed anywhere in the code, then surely it can be accessed anywhere in the code, and it can't be local?
Oh, she asked like the variable, like.
So malloc's scope. So you still need to have some sort of reference to the malloc's block of memory. So like here, we're returning x. If we didn't return x here and this were just void, then we would have no access to the pointer that was mallocked and it's leaked memory.
So like if you let's say you have this like right here.
No.
In my main function, I can't just call this x and be like, okay, in this function I did this. So I'm just going to call x in like main or something like that. You can't do that. You're going to return something, but what are you going to return? You're going to return a memory address. And because you return a memory address, that can be accessed elsewhere. Any more questions? Yes? Why do I not need to do that? Because you're not mallocing anything. So it's not, yeah, it's not like a string s that's a pointer somewhere. These are just values. Yeah.
And
anything else?
Yep. So in order to free the memory, we would say here, so x is our pointer to the block of memory. We free that pointer. And we wouldn't necessarily do it here. We could do it anywhere. But you only call free on something that malloc returns. So malloc here returned what is being stored in x. So we can call free on x. Any last questions?
Any last questions? Yeah. Free here? You probably don't want to free it here.
You probably wouldn't.
This would do nothing. This would like create memory, do stuff to it, and then immediately forget about it. Yeah.
But we might do something like in here for some reason. We might say int star y equals return array, do some stuff with y, maybe print the contents, and then finally we're done. We can free y. Ugh.
Do you want to scroll down? Okay,
all right,
that's it.
Good luck.
If you have questions, email us. Good luck.